Hello students, let us begin Module 6, Discrete Probability Distributions. Before anything, let's have some review. And this review is about Module 4 materials. Here's a definition of the probability. A probability is a set function defined in a sample space where each subset of the sample space is called an event, and it satisfies these three conditions. Number 1, the probability of any event is between 0 and 1. Number 2, the probability of empty event is 0, and the probability of entire sample space is 1. Number 3, the probability of disjoint union is the sum of the probabilities. What do you mean by disjoint? Here, we are talking about mutually exclusive events for arbitrary pair. For example, A3 and A10 cannot happen at the same time. And A5 and A17 cannot happen at the same time, and so on and so forth. Everything, every pair. In that case, we can sum up the probabilities, and that's the same as the disjoint union. This is the only non-trivial probability. This is the only non-trivial property. This one is too trivial. The probability of impossible event, the probability of absolutely certain event, everything is between 0 and 1, or 0% to 100% if you prefer percentages, because this is nothing that's whole, though. The third one, on the other hand, is non-trivial, so please beware. Here are some graphical explanations of some probabilities, some logical expressions. The probability of not A. From this picture, you can deduce that the probability of not A is 1 minus the probability of A. A and not A add up the entire sample space, and they're disjoint. You can clearly see that from this picture. So if you use the rule number 3 here, this one, and then the probability will be the disjoint union, which is the entire sample space. So that probability is 1. And using some algebra, we get the formula. How about this? Well, what if you have some overlap here? This one is for disjoint union. Here we have some overlap, as you can see. In that case, what do? You can decompose accordingly so that these three sets are now disjoint. A not B here, blue crescent, B not A over here, red crescent, and finally A and B, the purple in the middle. If you decompose into these three, then they are disjoint, so you can simply add up. Or you can do it like this. Probability of A, entire blue circle. Probability of B, entire red circle. And the purple part is counted twice, so we have to subtract it off. Either way, it works out. How about the probability of A intersection or A and B? Well, that's a middle part. And the probability is always between 0 and 1. Remember? Always between 0 and 1. And typically we use the multiplication rule for AND. So what do you get? Multiply two probabilities, you're going to get something smaller because you're multiplying a decimal between 0 and 1. So the more you multiply, the smaller the probability. In general, we have this kind of multiplication rule, and that's for conditional probability. And simpler case, when you have independent case, then you can just multiply straight up. This kind of thing without replacement and a bunch of others, and this one with replacement, and of course a bunch of other examples too. Okay, so much for the review. These things can get really deep really quickly, so let's stop here and let's move on to the real topic here, random variable. A random variable is a scheme to select some numerical values to each outcome of the sample space. The numerical value is typically called payoff, and easy way to understand it is gambling model. Here's an example. Let's keep it simple. We have an urn with 5 red balls, 3 green balls, and 2 blue balls. Total 10. Let's keep it simple so that we can calculate easily. The sample space is, of course, RGB, and please note that none of the outcome is a numerical value. And then what do? We assign numerical values to each of these, and here's one scheme. The random variable x assigns 0, 2, and 3 to R, G, B respectively. So here's a game. You get red, you get nothing. You get green, then you win $2. The ball you selected is blue, then you win $3. Here's another game. Select the ball. If it is red, you lose $1.50. If it's a green, then you win 50 cents. And if it is blue, then you win $1. And here's yet another game. So red or green, the same. You lose $1.25. Blue, then you win $4.75. Of course, there are all kind of other examples as well, but you see the picture. Even with the same model, same color distribution, same probability, same sample space, you can consider different random variables because random variable is basically a scheme. You can consider different schemes. 0, 2, 3 for this, negative 1.5, 0.51 for that, and negative 1.25, negative 1.25, 4.75 to this one, and of course there are many more. Based upon these, we can answer some questions, and let's answer. How about the probability of x less than or equal to 2? Alright, payoff has to be less than or equal to 2. Let's go over here. We have three possible values, 0, 2, or 3. And how can I get less than or equal to 2? There are two ways. Probability that x turns out to be 0, that's one way. Another is x turning out to be equal to 2. Is there any more? No, not really, because that doesn't qualify. So equal to 0, okay. And equal to 2, that's okay to 2. And is there any more? No, the only possibility is equal to 3, but that doesn't qualify. So what's the probability? Red or green? So what's the probability for red? 5/10. What's the probability for green? 3/10. So the answer is 8/10. Does it make sense? What if I change the problem slightly? Make it strictly less than 2. Now which one do we have? Equal to 0. Is it okay? 0 is less than 2, so that's okay. How about this? Green. Equal to 2. That's not okay. Here it's okay. Here no. So this one is no good. I have to remove it. Consequently, I have to remove this one as well. All these going out. And here's the answer. 5/10. How about the next example here? Probability of y is greater than 0 but less than or equal to 1. Okay, we have to consider the second random variable here. And the possible values are negative 1.5, 0.5, and 1. Anything else? No, that's about it. We have three colors, three possible outcomes, so we have just three numbers, right? And those are negative 1.5, 0.5, and 1 respectively. Now which one qualifies? How about this? Does it qualify? No, negative 1.5 is less than 0, so that doesn't qualify. How about the others? That's okay. That's okay too. And this is green. And this is blue. Make sense? For green ball, 0.5. For blue ball, 1. And the probability is 3/10 plus 2/10. So that's green. And that's blue. What if I change the problem just a little bit further? What if I change like this? Will that make some difference? What if I change this like this? Will that make any difference? Well, okay, I'll leave the details to you. Basically, what you do is go back here and then check which one qualifies and then add them up. That's basically it. The last problem here, oh, that's too trivial. I'll just open up. Either you have to have red or green, you see, negative 1.25 or this one, negative 1.25, either way. So 0.5 for red, 0.3 for green, and that's about it. Too simple there. What if we change all these? In this problem, what if I change these? Instead of 5 red balls, change it to say 7 red balls, change it to some other. What difference will it make? Will this part affect it? No, it won't, because that part is related to this scheme only. The color distribution will affect the probabilities, so this may change, that may change. Excuse me, let me be more specific here. Let's come back here. Where was I? Okay, all right. Let's change it to 7 red balls and 6 green balls and 2 blue balls. Okay, all right. 13, 15. There are total 15 balls now. And let's answer this question. Less than or equal to 2. So this is okay, and that's okay, and this is not okay. In other words, up to here, no change. But probability of red, now that's no longer 0.5. There are 7 red balls out of total 15 now. And green, there are total 6 green balls out of total 15. So the probability part is affected. And of course, you get something different here. 13 over 15 is the answer. All right. So I changed this part, and consequently this part was affected, but not that part. That part is related to these, the scheme, not that. So what's the moral of the story here? The random variable have 2 components basically. The scheme part, assigning real numbers, and then the probability part. This part, the scheme part, and then this part, probability part. Okay, is there anything anymore here? Not really. So that's about it. I'll say section 1 is done. Let's move on.